Everyone, our next speaker is Arshak Navruzyan. He is the founder of Startup.ML and organizer of this event. He's going to talk about machine learning approaches for startups. So please welcome Arshak.
Thank you, thank you, and thanks again to Bloomberg for having us here. A lot of hard work on their part went into this. A lot of fun on our part went into this. So I'm going to talk a little bit about Startup.ML. We're a new incubator. We've only been around for about 10 months. And our focus is how to bring machine learning to startups, both sort of very early stage and sort of in between, somewhat pre-funding, venture funded, et cetera, but not Fortune 1000 just yet. And our other objective is to, in the process of trying to solve that problem, grow the data science community, the machine learning community. In our humble estimation, it's way too small right now. And we'd like to find ways to be more inclusive. So what is machine learning to a company that has no data? And what does it mean when you only get the attention of investors and media, and to a certain extent even your potential users, when you can use machine learning as a buzzword, at least, if not actually demonstrate some real differentiated sort of functionality based on a probabilistic approach. So startups have a unique problem here. Some of this is also shared by mature data science teams, but I think the problem compounds when you don't have your own data or you're working on borrowed data. So all these things that we all know and on a day-to-day sort of do a hand-to-hand combat, trying to turn data into insights or products, we all suffer from these problems, right? We have very little data. The data has quality issues, labels, imbalanced class problems, sparsity problems, you name it, right? There's the canon of machine learning has a lot of these issues that we all recognize. But think about it in the context of you're going to battle all these same problems, but you have very little understanding of the use case you're trying to go after. You have a lot of sort of flexibility about what is it that I'm building, and you have very little data in that process. So it just becomes sort of exponentially worse for a startup to do machine learning. And at the same time, not only do you have all those classical problems to deal with, I think you have sort of a problem with the amount of options available to you in terms of things like software options. I'm sure you guys have seen this visualization, the periodic table of machine learning. This is probably just a fragment of what's available out there. There's 300 different machine learning packages. There's 30 different Python libraries for deep learning at this point alone. So again, startup, think about an entrepreneur that's maybe coming from classical sort of software engineering background, or even potentially even a business background, have to grapple with, what choice. Like I'm torn. Is it Theano? Is it Torch? Am I using, sort of single node distributed learning, Spark or Hadoop, or am I doing this in memory, out of core, et cetera? Lots of different options, and often this is kind of a waste of time, right? I think they focus a lot on this problem at the expense of trying to really understand the use case, figure out how do I get data, how do I make that data map to my use case in a meaningful way. What also sort of adds noise to this world is machine learning API companies and machine intelligence companies. Siobhan did a phenomenal job from Bloomberg Beta creating this sort of a map of that world. And she counted up almost 2,500 companies. Some of these I'm somewhat responsible for, and some she left out. So this is still only a portion of it. And I think there's a lot of, again, sort of mismatched expectations of vendors saying, oh, well, machine learning should just turn into an API, or we can make a GUI out of model building process, and that's going to facilitate this for you. And if you think about it, going back to those original problems that we talked about, where it's really about a human understanding the problem I'm trying to solve. What are the right input features? How do I overcome the sparsity of my data, or a lot of these other problems? It's very hard to fathom that software is just going to auto-magically solve all that. I mean, there have been some really interesting attempts, but I just don't think we're there yet. We don't have these sort of very general algorithms that can solve problems without human practitioners. So fundamentally, we think the way machine learning is going to get adopted by more organizations, and particularly young organizations, is somehow we have more qualified practitioners. We have more people that understand the fundamental principles of machine learning and data science, and can leverage all this, open source software and wonderful things going on to apply it. But you just cannot cut the human out of the loop. So the community is small, right? There's IDC said there's 11 million software engineers in the world. I'd be surprised if there are, 20, 30,000 qualified machine learning engineers in the world. So this is, if the trajectory of history is that a lot of software is going to become probabilistic in nature, we have to somehow bridge this divide, because most software engineering now is not done this way. So our involvement in this is essentially a fellowship program, but what differentiates our approach is the 4 months that our fellows spent with us, they're actually building a machine learning application, a real one. So that's either a project for a startup or an established data science team that's sort of discretized the problem for us to look into. The code is something that's going to go into production at the end of 4 months, so it's not a capstone project. So the level of complexity that they have to confront, the level of learning, we think is much better prepares them for going off into the real world to do this kind of work than the approach of teaching someone just from sort of a fixed curriculum, or saying the objective of this sort of bootcamp program is to just do a capstone project at the end, just pick a toy project. We think this sort of approach can bring a lot more rigor to the level of learning, and just seeing the trajectory of sort of our first cohort of fellows and what they went on to do, I think we feel somewhat reassured that we may be on the right path. So the background that you need to do machine learning, and I think this is one of the toughest problems that we face right now, is it's very much interdisciplinary. So first and foremost, you have to have some appreciation for machine learning theory. You have to have some background in stats. You have to be able to code. I just do not, I was VP of product management for Alpine Data Labs. So it was one of the very first sort of companies to claim that you can do drag and drop sort of machine learning. And yeah, I think those tools maybe do some things faster, but at the end of the day, real world problems still get solved when you're coding a machine learning problem, not dragging and dropping a machine learning problem. Optimization theory, I think, is important. Understanding distributed systems is important. You have to still do sort of discovery on your data before you start building any models. So being sort of graphically literate, being able to use visualization tools or create meaningful visualizations is important. And then I can't stress this last one enough, and I think this is another area where there's a huge shortage of skills, is soft skills, right? You can't be this sort of mathematician that doesn't like to deal with people, doesn't like to talk to the business, or you want to talk sort of above their head. You're not going to get anywhere. You're not going to accomplish anything. I can't tell you how many applicants we've turned down because we just don't feel like this person has that sort of soft skill to sell their ideas to the business side, or find partners that are going to work with him or her to champion the project. So this is very important, and I think particularly, given sort of academic regimes, et cetera, that people come out of, I'm not sure they get this muscle exercised very much. So you somewhat have to make this sort of choice. Do I want a really strong quant, or do I want that person to be more of a PM or a business analyst? We're trying to say you shouldn't have to choose, right? So, the pedigree of the folks that we see that want to come into the fellowship program, obviously ideal if you've done a machine learning PhD somewhere. The problem is there's, a handful of labs, like half a dozen labs where meaningful kind of work gets done in this area. So there's just not enough of those to go around. We see folks with stats and math background. We see obviously a lot of computer science people wanting to make this transition. And then even business analysts and PMs, my background is PM, or get very interested in this. So there's sort of spotty coverage, right? Everyone has sort of their strengths and weaknesses given that it's sort of interdisciplinary. So one thing we're trying, and it seems to be showing some promising results, is kind of do pair programming. When you're doing data science or machine learning, take a quant and pair them up with a software engineer. Or even take someone from the physical sciences, like some of our fellows from our last cohort had backgrounds like physics or poli-sci, et cetera. And we saw some really good sort of synergies when you ask them to pair program, because they overcome each other's shortcomings in the short run, and then in the long run, you hope that their skill sets sort of balance out a little bit. So from our last cohort, it was fairly small. It was only 6 people. You have a list of sort of their various backgrounds. We're really proud of their achievement. They've went on to do now data science at places like Analytic, which is Jeremy Howard's company, doing deep learning on medical imaging, Orange, Sentient Technologies, et cetera. So we're expanding the program. This is the mentor team. You'll see a lot of us sort of floating around. The mentors essentially facilitate the work, and sometimes we actually sort of in a very hands-on way, do the work with the fellows, but a lot of the time we're just sort of pointing, gently nudging them in a certain direction. Not always in the right direction, and a lot of rework, sometimes gets done, but just sort of benefiting from the experience of guys like GKB and Warren and Soups, having seen a lot of production data science at companies like A9 or Yelp, et cetera. So I'll share with you a little case study, and then I want to circle back to actually machine learning techniques that we think are meaningful and useful for young startups. So this case study is one of the fintech innovators. They brought us a discrete project. They're doing credit card refinance. So if I have some balance on my credit cards and I'm paying 24% interest, and I want to kind of get it down to more of a lending club Prosper level, I go and apply on their website and enter a minimal amount of information, and they can instantly make a credit decision and bring my interest rate down to whatever, 12% or 14%. So I think has some social benefit. So their sort of base model that they use in production has all the traditional features that you would expect, FICO, et cetera. But they have they have a desire to come up with additional signal without the trade-off being that if the more sort of questions and information that you ask of your user, the more likely they might just abandon, right? So that you can only get marketing to add that additional field on the input form if you can prove out that there's potentially really valuable signal here. So this is a classic example of cold start, right? We're not even collecting this data. How can we prove that if we collected this data, it would add value to our underwriting model in order to convince marketing to add this information? So I can't go into specifics as to what the information is, but it's sort of a sparse, challenging thing to incorporate into a model. And they have this competing objective. I think Gary already brought this up. Often when you're trying to create a model that has sort of modern method level of accuracy, things like neural nets or ensemble of decision trees, et cetera, it comes at the expense of you give up the ability to the transparency of the model. You're not going to see the parameters of the model. Well, in this sort of underwriting world, in particular when you're sort of hypothesis testing that this feature is going to add some additional signal to your model, you need that transparency, right? So the work our fellows did was really fascinating. They actually leveraged some work from Stanford. Jerome Friedman came up with this method that is primarily based on boosting. It's called rule fit or REGO, if you want to look up those packages. And it starts out as a boosting method, so creates trees and then calculates the residuals, creates additional trees. When all the sort of the boosting has been done, takes the rules of those trees and then actually runs a regularization over that, and then starts pruning all the trees that are not, or all the rules that are not actually adding any value. At the end of the day, then you have beautiful partial dependence plots that tell you, this particular rule is the most important. So, you're back, you have some level of visibility into what's going on with your model, and you have the predictive power of a modern, boosting method. So, this was done in a period of about 2 months by a pair of fellows, and they're actually, I think one of them is here. Daniel is a physicist, and Riwan is a kind of an economist or software engineer / economist. So it was fascinating for us to be able to experience this level of work, and it was fascinating to actually see their interaction with the in-house data science team. Like, the person leading this team is very experienced. The sort of the next lieutenant of the head of data science is one of the most prolific content authors for machine learning on YouTube, et cetera. So they already have a very strong data science team. And it was interesting to see their interaction with our fellows. So I'm going to try to summarize sort of all the lessons that we typically impart to our fellows, and some of you will just, this will be really, really obvious, and maybe some of it will not be. But the thing that we keep stressing to our fellows is machine learning is not about memorizing data. It's about learning something useful from the data. So generalization is, you should always keep that in mind because people forget that. So, very simple things like having a train test split or cross-validation, and remembering to do regularization, or in the case of things like RNNs, doing dropouts, et cetera. That's all, we all know these are the right things to do. Do we actually, how many times do we as the mentor team even forget that, we didn't do this step or that step? So I think this is sort of fairly important. I would call out actually one sort of interesting quote from a paper by Bergstra and Bengio, and they said hyperparameter optimization should just be considered a sort of a formal outer loop to all the machine learning that you're doing. I think now we treat it as a luxury, but as we switch to more and more of these sort of modern methods that do give us better predictions, it's becoming harder and harder for humans to have intuition about, out of all the settings that I have, for something like an MLP model or an RNN model, how do I make the best choices? So being familiar with like Bayesian optimization techniques, and that's one of the reasons we invited Scott to present. We think this is a really important area. So not only having a modern method, but then actually having sort of a black box optimizer that's driving the hyperparameters of that modern method is becoming sort of table stakes if you want to get good results. The other things that obviously we keep stressing are, go back to that sort of canon of all the different problems that you tend to see in machine learning and match that up against your method, right? Does this method, is it going to be able to handle the sparsity of my data? Is it going to be able to handle the fact that I have imbalanced classes, the fact that I have, I haven't normalized, et cetera. And again, I think this is something that we often forget to do. So, I want to have something that I can pass on to a software engineer founder as a sort of a cheat sheet on machine learning. And this is sort of the best that you might come up with. And I think it's useful, but it's also very confusing, right? I think a lot of these choices are maybe somewhat dated now. So we had Jeremy Howard actually come and speak with us. And the other extreme was that he said it's really simple. If you have structured data and you want to make good predictions, use an ensemble of decision trees. If you have unstructured data, do deep learning with these sort of flavors. And then the other sort of reinforcing factor here is this sort of hierarchy that Hasty and Cipriani came up with, which is Roosting can beat random forest, which beats bagging, which beats a single tree. And I'd be, I don't know how often we're working on a project that we're already using sort of XGBoost to create good results, and someone will come along and say, have you tried RF? It's like, no, Hasty and Cipriani have sort of done that work for us. We don't need to kind of go backwards in that hierarchy. So I think these sorts of high-level guidelines could be helpful to entrepreneurs so they don't get stuck in that sort of maze of the periodic table of machine learning. And we hope that we can keep, as a community, we can keep simplifying the options that we present to the outside world. Want to call out to one area that we think is sort of critically important or useful that actually Gary already brought up, and some of the work they're doing with RNNs and embeddings and things like Word2Vec. Some of the projects we've worked on recently, we've seen a pretty significant benefit to this approach of using a linguistic embedding with an RNN model compared to kind of what we consider to be state-of-the-art NLP currently. So I think this sort of broadly falls under this umbrella of transfer learning, right? So I learn an embedding using something like a Word2Vec, and then I take this sort of vector that represents linguistic relationships, and I use that in some other problem that I'm trying to solve. So my corpus can be completely different, right? I learn my embedding from Wikipedia, let's say, my initial Word2Vec model from Wikipedia data set. And now I'm going to apply it to, I'll use the example of some work that we did recently, which is we're going to take GitHub or Jira issues. I create a ticket in GitHub saying, I want this feature enhanced, or this feature has a bug in this particular project, and we're trying to build a classifier out of it. So if I get the text of any story, I want the algorithm to recognize is this a bug, an enhancement, or just a task, like a chore, as an example. So the reclass classifier. So, how do these embeddings get built? I'm sure, or these vector representations of words, I'm sure you guys have seen the Word2Vec papers, right? You have sort of a legitimate language in the sequence, and then it'll create a bunch of randomly mutated versions of that, where that sequence is not valid in the language. And then it forces the model to essentially create a vector representation that can correctly predict these. And there's sort of a continuous bag of words model and a skip n-gram kind of a model, or even an RNN model that'll actually produce this sort of vector representation of whatever corpus you happen to have used. So you take this model, first, obviously, you want to sort of baseline, right? Let's just see what like classical NLP does. My favorite tool for this stuff is WobbleWabbit. Right, it's super fast. You don't even have to do sort of TF-IDF. It can learn off of raw words. So all I do is I stop words remove, I stem the words, right? I have sort of a bag of words, and then it'll actually do the n-gramming, or I'll say, n-gram 3, skip 1, it'll do all that stuff. And then it does feature hashing internally, so I don't have to worry about having, tens of millions of features, right? So, and it's super fast. And linear learner, but it can learn 4 million features per second per CPU core. So we always do that, just sort of sanity check or baseline, where are we, like how well is this thing doing? And for our particular task, this 3-class classifier, we were getting about sort of mid-60 kind of results. And we have an imbalanced class problem, which means pretty much on 2 of our classes, we're making terrible predictions. So I'm sure a lot of you saw Andrei Karpathy's love letter to RNNs. And we're huge fans of RNNs as well, not only in this NLP area, but in some work we've been doing elsewhere in finance, has shown a lot of promise. So in a nutshell, the way we reframe the problem in this context is we start with this embedding. Typically, the bigger the embedding, the better. So somewhere between a 200-dimensional embedding to maybe, let's say, a 1,000-dimensional embedding gets trained with Word2Vec using your favorite corpus. You can even download these models sort of pre-trained if you don't want to waste the compute. You take this embedding and essentially kind of do your own projection. Like RNN is a sequence predictor, so you typically don't feed it sort of a tabular data set. You give it sort of a 3-dimensional matrix or a tensor. And sort of in this direction, you have all the different observations. You have still your words, and you can TF your words or give it a raw representation. And then what's adding the 3rd dimension to your data set is this embedding. Right, so you have this additional context about when does this word sort of occur in language. And then this allows you to now do this generalization because your weights don't get applied to that particular word in this particular example. It gets applied to that part of the language. So if you have a sparse NLP problem, right, this is hugely beneficial. So these sort of technical NLP problems like the one I described, where the vocabulary is very, very specialized. And your examples, there's very little sort of overlap from one example to the next as far as what part of the vocabulary this particular sample seems to be touching. This is hugely beneficial. Now I'll talk about something that's something we use in production now. It works great. This is something that we're sort of exploring and thinking about. There's a paper that came out of MIT called Enigma. How many of you saw that? Just out of curiosity. Cool. Okay. All the Startup.ML fellows, great. Drinking our own Kool-Aid. So what's promising about this is it combines a lot of different innovations. So blockchain is a component of this. Distributed machine learning is a component of this. Probably the most important component is multi-party compute. But basically, the idea is that if you string together enough of these technical innovations, you can actually do distributed machine learning over data sets that you don't necessarily have to bring together. So, 3 startups, 3 data scientists could say, let's kind of pool our learning. I'm not willing to share my data with you, but I'm willing to let you run some math over my data, and I'm going to do the same over your data. So this is an area that we're actively exploring, and we're trying to think out of all the finance startups that we work with that don't necessarily compete. One may be in this sort of unsecured lender, another one is in the mortgage area, another one's a hedge fund, et cetera. Could we possibly bring them together with some of this new technical advancements in MPC and other areas and create this sort of distributed multi-party machine learning? So these are some of the companies we work with currently. As I said, we're delighted by the projects that get brought to our lab. When we started this, we sort of envisioned that we would be useful to companies that had no data scientists and no machine learning engineers. It turned out that we're more useful to people that actually kind of have that well underway, and they want us to maybe explore some sort of shoot the moon idea, or they're very passionate about growing the data science community, and they understand that you can't just go back to this sort of ML PhD pedigree and insist on that in every case. You're not going to grow your team fast enough. So we're delighted to be working with all the names that you see up here. So that's sort of in a nutshell. Any questions? Great. Yeah.
How to get to the next level of knowledge? This is a great intro. You have events that
We do. So this particular event, we wanted to have it be a blend of more sort of use case, finance use case, and a little bit of machine learning. Our conferences are deeply technical, where you have to install Docker as the first step to getting admission to the conference and load a ton of machine learning software on your machine, and then walk through a lot of very specific examples. And in fact, you asked for this, so I'm going to plug it. We're going to have a conference in this building on November 9th at Yelp, where it'll be a much more technical conference. So we're inviting authors of deep learning software like Keras and OpenDeep, and people working in ensemble methods or hyperparameter optimization or probabilistic programming, to actually not come and give talks, but actually come and lead workshops. So like walk you through code, get the code running in your environment, and answer a lot of the technical questions. Great. All right. So we'll start lunch break early. Thank you.